So I develop high-performance computing tools for computational mechanics. So I've worked professionally as developing high-performance computational tools at Sandia National Labs before I came to Texas. Throughout my PhD research and postdoctoral research, I've been developing these tools also. In this framework, I also develop computational modeling of material failure and mechanics. So what I'll be talking about today is the model that we've developed for predicting crack growth. And also I develop and leverage state-of-the-art numerical methods. One example, if you've ever been to Texas, you've heard of isogeometric analysis. This is an extension of finite element analysis to using basically the same description for the analysis as used in geometry tools that build the analysis models. So as at Sandia National Labs, we had what we were called heroic problems. And heroic problems were these problems where we wanted to push the boundary of everything that we did at Sandia, whether it was the material modeling, building the geometry models, the meshes, and doing very large-scale simulations. In my work, I've defined a heroic problem as simulating hydraulic fracturing. So in hydraulic fracturing, what they do is they have these shell formations that are have natural gas reserves that are trapped in the porous material of the shell. And so what they'll do is they'll drill a well down into here, and then they'll pump this well with fluid and pressurize the shell formation to develop cracks. Why is this problem so difficult? Well, first of all, the scale of the problem. We have these formations that are on the order of kilometers, and we want to model crack opening widths that are on the order of millimeters. So we have huge discrepancy in scale of what we're trying to model on the large scale and what we're trying to model on the small scale with the crack opening. We also get complex 3D crack topologies. So we have cracks that are growing in 3D, that are branching, they're merging, they're intersecting with each other. There's also the complexity of the physics. So we couple our flow with our fracture. We also have out in the unfractured area, there's this Darcy flow regime that must transfer in a consistent way into Stokes flow inside the channel. So there's a coupling between the fracture and crack growth and the fluid, and also the transition of the fluid flow from one regime to another. So how are we going to solve this problem? Well, the solution is with the phase field models we have. These phase field models will handle 3D cracks. We have a thermodynamically consistent way of coupling the physics of the crack growth and the fluid interaction. We've developed a higher order convergence theory for crack growth, where we use smooth basis, and I'll just briefly describe what this means from isogeometric analysis. We do adaptive refinement, which maintains the smoothness that we need. And high-performance computing comes into place because the length scales here are going to dictate billions of degrees of freedom. I'm going to have some way to do this to compute these large-scale systems. So with that introduction, I'll get into the more technical content of my presentation. First of all, I'll introduce the phase field model, and we'll talk about the formulation for dynamic brittle fracture. I'll give some numerical examples. Some of this may seem like deja vu to some of you who were here in November when Tom Hughes came and gave a seminar. He talked about a lot of these same things. I'm going to go over it again to set the stage. I'll talk about a higher order fracture model. Then I'll go into some future work that I want to push this into. Again, hydraulic fracturing, and then some other future directions I'll just briefly describe and then sum things up. So when I think about fracture models, I like to group them, maybe oversimplified, but group them into two different categories. The first category is discrete models. Think of something like XFIM, or element deletion cohesive segments. And the idea here is that we want to track a small number of distinct cracks. So small is something where we can actually see the crack. We want to see how it grows and how it affects the overall structure. One of the problems with this is it's very difficult to extend this into 3D, where we have intersecting cracks especially, or complex topology. I mean, it's difficult to compute those intersections in a robust way. The other grouping is what I call smeared models. These would be continuum damage models. And the idea here is you average, in some way, many small cracks. And this is a popular method for doing something like concrete, where you get this cracking in a kind of a localized reduction of strength in the material. But the nice thing is there's no boundary tracking. And so we want to combine the strength of both of these methods into a single methodology, and this is where the phase field model comes into play. What we're going to do is we're going to resolve cracks down to some length scale that either is a material well, I'll show it. It comes out as a material parameter. Where we get dominant cracks, this length scale we call L naught. So here, for example, this black line would be our discrete crack that we're trying to approximate with a phase field. And so we have some phase field, which is just a scalar field, and around the crack area, that scalar field is equal to 0, which means we have no strength. Away from the crack, the phase field is equal to 1 where we have strength. Then there's some transition between the two. Right, so we can resolve these cracks down to some length scale, but we also can avoid tracking the interface. So we remove some of the complexity that you get for the numerical implementation. And in fact, this becomes very simple to implement, and it extends trivially to 3 dimensions. So just an example to see what this looks like for getting into all the details. So here we just take an example of a pre-notched rectangular specimen, and we're just going to apply a traction to the top and the bottom surface and pull this apart. So here we have, this is the phase field, so this is the initial crack modeled in the phase field, where the red is. Down here is a post-process view where we've removed the visualization of where the crack is. The one thing I want to point out is all this calculation I'm going to show is done on the original mesh. The mesh does not change. And so we'll just show it here. So here you can see that the crack begins to propagate. We get some branching where there is there's a buildup of energy. It needs to release more energy. We get a crack branching. And this happens completely described. This branching behavior, the nucleation, the propagation behavior is completely described by the model. There's no indication in there that says this is when the model needs to branch, or this is the direction the crack needs to go. And I'll show you what the model is here. So to develop our model, we start with with Griffith's brittle fracture theory, where we have an energy that describes our system, and that energy includes the strain energy of the system plus the crack energy of the system along some path. And what we want to do to solve this problem, we want to use a variational approach which minimizes the energy. The problem is if we just look at this, trying to minimize this as it is here, we have an infinite number of potential crack paths that we try to minimize over. So it becomes computationally intractable. So to make this a problem that we can actually compute, we introduce a phase field approximation. The phase field approximation looks like this. So here's our original potential energy. What we've done is we've now taken this integral over the surface, and we've approximated it by some what we call crack density functional, which is an integral over the volume. So now we have an approximation of our crack, which is this algebraic term of our phase field. Again, when c equals 0, we have a crack. When c equals 1, there's no crack. So this term disappears when there's no crack. And then we have some term here which takes into effect the gradients of the phase field. And then for the strain energy, we do a decomposition where we have a compressive, this is the compressive component of the strain energy, and a tensile component. And then we have this function we call a degradation function, which is only going to reduce the strength of the tensile component of the strain energy. And we find this important in a lot of cases that if you're reducing the compressive strength, especially in dynamics where you have stress waves, that you'll get spurious cracks where you get some kind of a compressive stress peak. And so it's important to have this decomposition. And this, just to show what this looks like, it's based on a additive decomposition of the strain energy. So here's our typical strain energy. We want to decompose it into a tensile part and a compressive part. The tensile part looks like this, where these angle brackets are just taking the positive part of the argument. So it's taking the positive trace, and then we have what we call our tensile strain and our compressive strain. And these are computed using a spectral decomposition of the strain here, where this is just taking the positive part is just the sum of the positive eigenvalues and their bases, and the eigenbases. And then we get our damaged elastic strain. And of course, then we just plug this in and we get this is how we would compute the stress, damage stress. So we run this through the typical machinery to come up with our strong form of our problem. So again, here's our free energy. The stress now is defined as this, where we have our phase field is now a function of we have a degradation function, which is a function of the phase field. Plug that into our linear momentum function, and then we have a phase field equation that looks like this, where the evolution of the phase field is driven by the tensile part of our strain energy. Now this degradation function, the typical one is the quadratic function. It looks like this. So as c goes to 0, we get a 0 value for our degradation function. It has a 0 slope here, and then it goes to 1 at 1. And we can do an approximation of this function by dropping the gradient terms of the phase field. And if we do this, then we can solve the 1D problem. And we come up with an equation for our stress in terms of our strain, and we can plot this function. We get something that looks like this, where we have it as we increase in strain, our stress goes up. We hit some peak stress, which we call the critical stress. And then the stress drops off as we continue to increase the strain. And I want to point out that this critical stress is a function of our material properties and our length scale. As this length scale goes to 0, of course, our critical stress will go off to infinity, which would then converge to our brittle fracture theory. But we look at this, and we look at this dependence of the critical stress on the length scale, and we say that length scale is also a material property. And we can compare this to, we can make a comparison to existing theories for fracture. So if you look at brittle fracture, the theory of brittle fracture says that a crack will grow. If you have a crack at the crack tip, if you look at the stresses in front of the crack tip as a function of the radius, as that radius goes to 0, the stress will go off to infinity. That's the only way you'll get any kind of growth or nucleation of your crack. To handle this in a more realistic way, we introduced a cohesive zone in front of the crack where we say, okay, we're going to limit that stress to some amount, some magnitude of stress. So we're going to cut that stress off. So now we can get nucleation propagation at some finite stress. But this introduces this length scale, this process zone. If you look at the phase field theory, it's similar, right? So we have, if we look at the crack and look at the stress in front of the crack, we have an increase in our stress that reaches some peak stress, not necessarily equal to this critical stress, but related to it, and then it drops off. But we have, again, you see that there's this process zone. And if you look at a model, say for instance a simple Dugdale model, where you have this process zone as a function of our stress intensity factor, we can rewrite that in terms of our other material parameters, this crack energy density function in our Young's modulus, and also this peak stress. If we approximate this peak stress with this critical stress, we get a relationship between the process zone for this cohesive model and also the process zone is L naught for our fracture model. So there's some relationship there. We haven't really figured out all the details of it. But introducing this phase field model, in a way it's introducing a new cohesive type model where you have a process zone in front of a crack tip that allows these cracks to propagate and initiate at finite stresses. So let's go back to this example again. I've already showed you the one animation of it. And we can do some mesh refinement studies. So we look at the same crack pattern, the same material properties, so the length scale stays the same. And we just refine our mesh. You can see that under this mesh refinement that the topology and the behavior of the crack is very similar. So you can see that there's some better detail for a finer mesh, but overall they look the same, which indicates there's some mesh independence, at least under refinement for this model. We can also look at global measures for these models. So here's a plot of the elastic strain energy over time for this problem. And again, you can see that there's some convergence, but also it's very stable under mesh refinement. So very good agreement between different levels of mesh refinement. We can also look at crack tip velocity. Now, in brittle fracture, there's a theory that says that the maximum speed at the crack tip is going to be 60% of your Rayleigh wave speed, which is up here. Experiments for these type of materials that we're modeling here, the experiments say it's closer to 40%. So you can see that our model is doing very good at capturing the crack tip speed for these for this example. And also you can see that under mesh refinement that the stability of this crack tip velocity. So this is an example that, just to demonstrate the complexity of the type of crack problems we can model. So this is the same one before. I've increased the applied traction, and we're going to let this thing run for a longer amount of time. So we let it go, the crack begins to nucleate, it branches, it'll do branching again. And then as it hits the end, the dynamics of the problem, the stresses keep reflecting through the model. We get some buildup of stress. And we get the secondary cracking, where we get additional branching and intersection and merging of the curves. So just a brief summary of what I've talked about so far. Right, so we've introduced the phase field model. It has no interface tracking, so it's a robust numerical implementation. It's robust in both 2-dimension and 3-dimension. It automatically handles nucleation, propagation, and branching, these complex crack topologies. The question is, can we get higher order convergence? And can we improve the accuracy of this model? And of course the answer is yes, otherwise I wouldn't ask it up here. So this goes into, what is our higher order model for fracture? What are we trying to do? Well, to get better convergence, better approximation properties, there's two things you need to do. First of all, you need to increase the polynomial order of your basis functions, or your approximation space. Right? And this can be done by either C0 finite elements, so these are the typical quadratic Lagrange basis functions, or you can go up to B-splines. The other part of it, of accuracy, is the regularity of the exact solution you're approximating. Now with the phase field, in order to get more regularity, we have to introduce additional derivatives on the equation, which requires a smooth basis. So here we have to go up to a smoother basis function, which is provided by B-splines. Another thing I just want to point out, that these kind of basis functions have showed that they also increase numerical stability in a lot of cases, increased accuracy. Another thing that may be an interest here is they provide continuity. So you get these continuous spaces, which makes it very easy to implement gradient theories. So you can do strain gradient theories with just displacement degrees of freedom. You don't have to track any additional degrees of freedom or have any type of mixed formulations. So let's look at the higher order theories. So now we introduce what we call a fourth order theory. So this is the phase field equation that we had before. We introduce a fourth order theory where now we've added in this additional term, which has an additional derivative on the phase field. So we've increased this will increase the regularity of our solution and also increases the demand for smoothness on our basis function. So what do these look like? So if we just look at the 1D profiles of what the exact solution of these problems would look like. So our second order here, we have the blue line would be where the crack is. We have some kind of diffuse approximation, but we have a cusp. We have these additional derivatives, and we get a smooth approximation here. And that additional smoothness provides the potential of higher order accuracy. Now you might look at the second term here, and you'll see there's a difference in the coefficients. This algebraic term is the same in both cases. But why are these coefficients different? Well, we adjust the coefficients so that in 1D, we get the exact energy from the crack. So if we're doing a 1D problem, we get the exact energy in both cases. Here's the strong form again. Everything up here is the same. This is the same as before. Here's the fourth order. Now we have 4 derivatives on our phase field, which means in the weak form we require 2 derivatives, which means we need a smoother basis function. So we want to do, so what do we get? Does this actually improve our model? And the answer is yes. And so I want to do this as just do a simple 1D analysis to show what kind of improvements we get. And the idea is this. Think of a 1D bar example where you've got it fixed on one end. It's cracked completely through the center crack. And then you displace the other end. All right, since that crack is in the middle, you should get no strain energy in the model. And you should have the surface energy of the crack would be the only energy contributions to the model. So we do this in a decoupled way. First of all, we fix our phase field, or our C, And then we're going to just solve the equilibrium equation with this field specified, given. So we do this for the second order. This is the phase field problem. Again, this is the solution we've seen before. And in the fourth order, we plug this guy into the equation. And then we measure our strain energy. Notice in our strain energy, we have this phase field parameter shows up. And if we do that and look at convergence, we see as we decrease our mesh size, the second order, we get a convergence weight of 1/2. The fourth order converges at 1.5. So we get better convergence with our fourth order theory. So it's going to provide better accuracy in our strain energy. We do something similar for the surface energy, where now we set epsilon to a delta sequence, and then we solve exactly the phase field equation. So now epsilon is given, and we can take different epsilons. We can take a discontinuous strain field, which would be the result of using a C0 finite element linear basis, or we can do this linear continuous basis, which would be the result of using quadratic basis. We plug these into our phase field equations, and now we're going to solve for the surface energy. And again, second order theory gives us a convergence of one weight. Fourth order theory, we get better convergence. So we get more accuracy in our surface energy. So that was a simple 1D uncoupled problem. So we want to look at this now in a more realistic setting. So we look at a two-dimensional problem. And we're going to look at a double cantilever beam example. What we're going to do, we give a displacement, some change in displacement. We give our critical surface energy here. And then we're going to solve. We're going to compute the change in this is a crack surface energy, sorry. The change in the surface, we're going to compute the change in the surface energy from our initial displacement to our second displacement. And then we're going to divide that by the change in the crack length. And we'll get out what we call an effective critical fracture energy. And we're going to compare that to the material parameter that we put into the model to see how they compare. And we do this on double cantilever beam because the crack growth is stable here. So if we take the two ends and we displace them a small amount, the crack will grow a small amount. So that here just is a picture of the mesh. We're using some kind of refinement strategy here. It's all smooth. We look at the convergence rate, and we see for the second order theory, we're getting linear convergence, which agrees with the 1D, one-dimensional case. Fourth order theory, we're approaching convergence rates of 3, which agrees again with the one-dimensional case. So we're improving our accuracy with these models, and it shows up in this more complex second two-degree case, two-dimensional case. So again, a summary of what we've talked about. Okay, we use the smooth basis from the isogeometric analysis framework to allow us to solve problems with higher degrees, higher derivatives, which require the smoother basis. And we can do this efficiently. We don't introduce any additional degrees of freedom. Also, the higher order theory, the fourth order theory, we have it improves the convergence rate for our fracture problems. So now I want to get into kind of where we are going with this model, where I plan to push this model in the future. So let's go back to the hydraulic fracturing problem. Again, with all of the challenges that we have the length scale challenges, the complex 3D topology of the crack, and also the coupled physics problems. And here's just a summary of some of the things that we'll have to deal with. Right, we have to be able to handle pressurized cracks. We pressurize a crack, we expect the crack to grow. We need to handle the flow between the transition between Darcy and Stokes flow. We need to be able to handle flow through opening cracks. As the crack gets wider, we expect more fluid to flow through it. And we need to be able to handle the complex 3D crack topology. In the high performance computing aspect of it, we need to be able to do large scale computations. And this is where the higher order accuracy will come into play, because we'll be able to do this with less resolution than we would require with the other models. And also we need to do some kind of adaptive refinement using a smooth basis. So looking at pressurized cracks, a simple way to do pressurized cracks is to first we look at the linear momentum, the weak form. We look at the body force and we say, okay, we're going to apply a body force that's a function of a pressure and also the phase field. So you see the phase field is equal to 1 when there's no damage. We'll have no pressure gradient. If it's equal to 0, then we'll have a pressure gradient will show up in our equations. The weak form will look like this. So now here we have the pressure shows up, and then we have some boundary conditions with the pressure. And we can run some simulations where we've done some simple simulations where now we have an initial crack. It starts with an initial crack here in both cases. We apply a pressure field throughout the volume, so the pressure is now applied only on the crack, and we get, for one level of pressure, we get a straight crack. No, we can increase the pressure and we can get different crack topologies. So we can apply pressure to these cracks, and we can apply it as it's growing, and there's nothing that we need to do to say this is where the pressure needs to be applied. We don't need to set up any additional boundary conditions as these things are growing. It just comes naturally out of the formulation. So let's look at the governing equations now for the fracking problem. So we said we can do pressurized cracks. Here we see, if we define our stress, here's our pressure term that we had in our weak form. Now we show it here in the stress. We have equilibrium. Again, this is just the equilibrium of the solid. This is just a compact way of writing the phase field equations, where these terms are now defined like this. We have fluid equilibrium, which we have a term that's here, the stress for Stokes flow, defined over here. We have a body force, which is the solid. There's a force applied to the fluid from the solid, which is now some kind of a Darcy term. And then we have fluid incompressibility here, where we look at 1 minus C as the porosity. If we look closely at these equations, this is how the coupling works, okay? So we have a pressure in our fluid equilibrium, and it's coupled with the stress through this term. So we have the kind of the fluid acting on the aggregate through the pressure. We have the aggregate acting on the fluid through this term, which is again the solid, the force on the fluid that is from the solid. And then we have a coupling or transition between Darcy flow and Stokes flow here, where the phase field comes into play. So the phase field is 0. Our Darcy flow term goes away, and we have Stokes flow only. When the phase field is 1, so if the phase field is 1, then this term goes away, and we have only Darcy flow. And then there's a transition between the two, and it happens consistently. So how does this look? So we do a simple 1D flow through an opening crack. So what we'll do here is we're going to apply uniform pressure on the left over here and a 0 pressure on the right. And we have one element in here that's totally damaged. And then we have some computation in there we have some over-resolution of the fluid part inside that's damaged. There's some coupling that goes on between the meshes that I'm not going to get into now. But then the gap is opened, and we want to see what happens to the flow profile as that crack is opening. So here's just another picture. This is the mesh again, and you see as that crack opens that the fluid flow, we get an increase in the fluid flow profile. So here's the phase field in the red. There's actually a non-zero flow here in the Darcy flow in the away from the crack, which transitions, this is very small so you can't see it, transitions into a Stokes flow inside the crack. And then when it gets up, so here's a comparison to the ideal analytical solution, which is the red, and the numerical solution in blue. So with this model, we can couple the flow in the porous media with the solid. We can get the transition between the porous media and the channel. We can do that consistently. One of the other challenges now is 3D crack topologies in the porous media. So here's a different example. This is not with hydraulic fracturing, but this is a 3D example where we take this cube. So these are just different views of the same geometry. And we introduce what we call nucleation sites. These little red spots are areas where the phase field is set to 0. So there are weaknesses in the material. And then we're going to just apply displacements to the top and bottom, and we're going to pull it apart. One thing I want to point out here is that we're doing 16 million quadratic elements. We're using our 4th order phase field theory. So this is a very large problem. This is starting to get heavy-duty computing. These are, again, our quadratic elements. 16 million elements means there's close to, what is that, 64 million degrees of freedom in this problem. So I'm just going to show the animation. Now remember, we're pulling the top and the bottom apart. You can see the crack begins the nucleus here begins to propagate. We get areas where there are intersecting cracks. We get additional multiple crack fronts that develop. We get this complex branching topology. And all of this, again, is just done with, all of this is, again, just determined by those two equations that I have, the equilibrium equation, or the momentum equation, I guess in this case, and the phase field equation. There's nothing in there in the model that says we need to branch here, we need to go this direction, we need to start nucleating a crack at this point. It's just a solution of those two equations. So another challenge now is that mesh that I just showed was a uniform mesh. If we try to do a uniform mesh on a full hydraulic fracturing problem, it would be too big to compute. And so what we need to do is some kind of refinement. And we can do this hierarchical refinement on B-splines, where we find certain areas of our splines with refined functions. And we do this in a way that maintains linear independence, and we can compute with it. But this is something like what it would look like. These would be the initial basis functions. We have one level of refinement where we remove these basis functions because they're represented in the lower level basis functions. And we go down to several levels. So here's an example. This is a phase field tumor growth model, which I've worked on with another colleague. And you'll see that we can do additive hierarchical adaptivity on these splines. You'll see, here's the mesh. We're going to do both refinement and coarsening. You'll see as when I play the video, as the front propagates, you'll see that it adds in functions and it takes them out when it doesn't need them. And so here you can see it starts to propagate. It does some kind of lob. You can see how we have a refined area here. You can see that the refinement is being removed as that front passes through the mesh. And one thing I should point out too is that this is maintaining the smoothness of the basis function, so we can still use our higher order models for these meshes. So again, just to summarize, what have I shown? So I've talked about the hydraulic fracturing problem. This is the problem that we want to do, and we've got a good start on it. But there's still a lot of work to do. But we can do the physics and the mechanics of the problem. We have examples that show that we're on the right track. There may be some more work to do to get everything correctly done correct. And also we have examples of the tools that we need to do the high performance computing, the large scale computations. We just need to put all these together, and in a number of years, I think that we'll be able to attack this full scale problem. So some other examples of future work that we want to go to, and one is ductile fracture. And we've done some initial work on this, which is a purely phenomenological model, where we say before, if you remember before, we had this term which just included our elastic strain energy. We say, well, what if we drive the crack growth also by some plastic work term? And we use these two parameters, say we can kind of do some combination of the two. One thing I should point out is that there's still work to do here. For example, this doesn't include any idea of triaxiality, which has been shown that experiments have shown that this is an important part of the fracture process. Also, we don't have any kind of way of modeling void growth or coalescence. So to really get this more physically accurate, we'd have to include some terms in here that have something that we could include something from a Gerson model, perhaps, using some ideas from this hydraulic fracturing problem, where you can talk about this, the porosity of the model and the void fraction volume in terms of the phase field, right? But just using the model that we have, where we have this combination of elastic strain energy and plastic work, you can vary these parameters and get different behavior. Really, the best one that we've found in our examples is where you're just combining the two in a linear combination. Here's an example of something that we really want that we're pushing towards. It's interest to some of our funding agencies at Texas, where we have where they've done an experiment. We're taking these steel plates, and these things are about 1 meter in diameter, so they're fairly large. They bolt them to a reaction frame. They put them underwater, and they set off some charge in front of them. And so there's a lot going on. We've simplified the model to begin with, but here's an example. So we start off with the plate, and we let it, and we apply a pressure, and you can see that we're getting these crack growth. We get ductile, the deformation. You see that the bolt's broke, and then we get this behavior, and qualitatively at least, we get some very good results. Where you can see where here on the corners we get some kind of buckling. You can see if you can see it back there. you get a similar view, a similar thing happens here in experiments. So another thing that I've just started to think about and talk about with a collaborator who's at Texas Heart Institute now is thinking about some ideas of modeling vulnerable plaque rupture. And we're just getting into this, and I don't understand all of the aspects, the physiological or physics aspects of it. But vulnerable plaques, if you look at the medical statistics in the US, heart attacks are a huge problem. 500,000 people a year suffer fatal heart attacks. Another 600,000 have non-fatal heart attacks with the associated medical costs and the degradation of the quality of life. And these heart attacks are caused by plaque buildup in the coronary arteries, which then block blood flow and oxygen to the heart, and then it causes damage and death of the heart tissue. And 70% of these heart attacks are caused by a rupture of plaque. And so what happens is you have this inner layer of the coronary artery, and you get this buildup of the LDL cholesterol, which creates this, they call it a lipid core, which is surrounded by some kind of a fibrous cap. And as this thing grows, this cap here begins to thin and stretch, and it gets an increase in pressure, and eventually that will rupture. And currently, in the medical profession, the way it's based on diagnosing these or determining what kind of treatment is based on experience and kind of the doctors involved, what they think needs to be happened. If they need to do some kind of intrusive in treatment to try to treat these things, which has its own could have its own negative side effects. We'd like to develop some computational tools that will help us not only understand how these things develop and form and eventually rupture, but also in the long term perhaps provide some kind of numerical tool for doctors in evaluating the treatment that is necessary for these. Just some other ideas for future work. I know that from what I understand from a few conversations is that the study of lithium batteries is very important here, and it's very important on a national level and from an energy standpoint. Where fracture, from what I understand about batteries, is development of fracture that degrades the capacity of batteries to hold a charge. I think that the tools that we have, that I've been developing, these phase field models, are ideally suited for modeling some of these processes in lithium batteries. Again, related to vulnerable plaque rupture is also aneurysm rupture. As these things, if you know what an aneurysm is, it's a deformation on a blood vessel that will grow, and if these things rupture, especially if they happen inside the brain, they can cause a lot of serious problems. Here I have some pictures here. Another thing is blast and fragmentation. So we see that we can do these complex crack topologies. We can do large deformation models with our phase field models. I should point out again that this is all done on the original mesh. You don't see the elements in here, but if I draw the elements, there's one element through that crack that's being stretched out, and we can handle that effectively. There may be some other interest. There's some other work that we'd have to do. We'd have to develop some more fluid structure interaction type formulations to get this correct. Another idea is just anisotropic materials, say for instance concrete or composites where you have a phase field. You may have to add additional phase fields to get different direction or different behavior from the composites. This idea that I talked about with ductile fracture, where we add in a term from the plastic work. Another thing possible is to do multi-scale models, where you have some kind of additional to the crack, additional contributions to this function from multi-scale models, and where the phase field can indicate which models are active and which models are not active. And of course, using the smooth basis, developing numerical methods for gradient theories, where we have this technology which allows us to compute these types of models with just the displacement degrees of freedom, and which is the standard formulation. We don't have to introduce any other additional degrees of freedom or do any mixed type formulations. Okay, just in summary and conclusion. So what I've showed today is a phase field description for fracture that automatically handles nucleation, propagation, and branching of cracks. I've shown a fourth order theory, which gives us improves the strain and surface integer approximation. So we get a more accurate model of our crack formation. We can do complex evolving crack topologies in both 2 and 3 dimensions. And possible future directions that we're pushing towards are in the energy related. We've got fracking and batteries, biorelated vulnerable plaque and aneurysm rupture. And there's many more things that these type of models could be applied to. And I think that there's a lot of promise in using these phase field approaches to kind of reformulate some of the theories that we have now in a new perspective, which includes a phase field. And along with that, it brings an opportunity to really try to develop and understand the mechanics and the physics that are implied by this reformulation of these models. I think there's a lot of potential for this type of work and these type of computational models. So with that, I thank you.